Thanks. Thanks, Shiraz.
Okay, thank you.
Thanks. So Onkar Parrikar is the next speaker. Onkar, you must be online.
Yes, I'm here. Let me just share my screen.
Yeah, sure. Okay, so the last speaker of this morning session is Onkar Parrikar. He will tell us about quantum error correction in the black hole interior.
Can you see my screen?
Yeah, just go to the first page here.
Oh, sure.
Perfect. Yeah, okay. Start. Please go.
Great. Thank you so much. Thank you for the invitation to speak at this wonderful meeting. So I wanted to tell you about some work I've been doing with 𝗰𝗵𝗶𝗿, Arjun Kar, and Kathy Lee on the quantum error correction in the black hole interior. So recent progress on evaporating black holes has shown that after the page time, a portion of the black hole interior, namely the island, is encoded in the radiation. There have been several papers on this subject, and I've only listed a few here. But the setup of these calculations roughly involves some holographic quantum system, which I'm going to try and call B throughout this talk. So this B, we can think of the state of B, or one could think of as being sort of holographically dual to a black hole. And then this quantum system B is coupled to a bath, let's call it R, which absorbs the radiation. Okay. And as I said, the semi-classical dual description consists of this black hole dual to B radiating into the bath. And these calculations, as you all know, show that after the page time, a new quantum extremal surface develops in the space-time dual to B, and the portion, the island part of the space-time moves over to the entanglement wedge of the bath. Now, a quantum error correction provides the sort of underlying framework for entanglement wedge reconstruction, and the sort of most familiar setup in which this is well understood is, for example, when you have some quantum extremal surface in the bulk spacetime, and then the entanglement wedge, namely the sort of domain of dependence of the region enclosed between this QES and the boundary subregion A, is encoded. So the degrees of freedom in the entanglement wedge of some boundary subregion A are encoded in A, such that any errors happening on A complement do not affect the degrees of freedom in the entanglement wedge of A. Now, in the context of the island, we expect a very similar encoding where the semi-classical degrees of freedom in the island would be expected or are encoded in this way in the radiation Hilbert space. But in this talk, we wish to understand how robust this particular encoding is against quantum errors acting on the radiation or on the bath, okay, motivated by the results in this recent nice work by Kim, Preskill, and Tang. Now, just to point out that the kind of errors that we are interested in exploring here occur on the same boundary factor, namely the bath, where the island is encoded. So this quantum error correction is a slightly different and a slightly more robust version of error correction than the one that's perhaps more familiar in ADR-CFT. Okay, so let me just begin with a small overview of the sort of framework behind quantum error correction. So the setup involves sort of an encoding of a smaller Hilbert space, which we might call the code subspace, into a larger Hilbert space, which I'm calling here the physical Hilbert space. Okay, so this encoding map V is an isometry, namely it preserves inner products. And the general theory of quantum error correction deals with the question of when can we recover these encoded states from the physical system after the potential action of some errors on the physical system. Sorry. Now, in this context, an error is modeled by some quantum channel, which I'm calling E, you can think of a quantum channel as a sort of generalized quantum operation, which maps density matrices on H physical to other density matrices on H physical. I'll give a more explicit description of quantum channels in the next slide. But the idea is to model errors happening on the physical system by quantum channels, and then ask, well, when is the encoded state preserved under such errors? Now, as I said, we can think of the action of any quantum channel E, a very general quantum channel E, in terms of an ancillary or auxiliary environment factor. So we imagine that there is some auxiliary Hilbert space, namely the environment Hilbert space, which sort of is brought in some fiducial state, which I'm calling E0 here. And the action of this quantum channel on some density matrix rho on the physical Hilbert space is given by sort of acting on the joint system, the original density matrix rho, together with this auxiliary state on the environment, then act on the full system by some unitary transformation U, and then trace out the environment. Okay, so you can think of this environment as some sort of noise that is some external noise that is introduced by this particular coupling U. And so this is the most general form of a quantum channel that we will consider. And we say that an error E can be corrected if there exists a recovery channel R, such that R acting.
I have a question.
Yes, please.
So is the environment density matrix, environment channel density matrix, a pure state? Is considered of pure states?
Yeah. So in this case, I'm considering it to be a pure state. It doesn't have to be, but it's without loss of generality. You can always take E0 to be a pure state, because if it weren't, then you could always purify by introducing a bigger environment.
But I would guess that an environment usually would be something that is kind of random or something, right? Because even as it is like a path.
That's right. So even if it is, you're right, but even if it is a mixed state, then you can always purify that by introducing some auxiliary, some more environment degrees of freedom, and then consider that to be your new environment state, the auxiliary state that you're bringing in. So what I'm saying is that without loss of generality, you can always write any quantum channel in this way, where just for simplicity, I'm taking E0 to be a pure state, but it doesn't have to be. Okay. Without loss of generality, you can always write it this way. Okay. So as I was saying, we say that this error channel E can be corrected on the code subspace, provided there exists a recovery channel R, such that R acting on E acting on rho gives back rho for all density matrices which have support on the code subspace. Okay. Now, one of the central results of the theory of quantum error correction is a sort of nice and interesting condition for when an error is correctable. So in order to tell you this condition, I have to introduce another sort of references, which we're going to call a reference system, href. This reference system is isomorphic to the code subspace, namely the subspace of states that, or the space of states that you want to encode in the physical Hilbert space. And having introduced this reference system, what you do is you basically consider sort of the maximally entangled state between the reference and the physical Hilbert space. So here the capital psi i's are the encoded states in the physical Hilbert space. So you consider, roughly speaking, the maximally entangled state between the reference and the physical Hilbert space, and then you act on this joint system with your quantum channel. Okay, so the action of this unitary U on the physical Hilbert space and the environment factor is sort of implementing your quantum channel on the physical Hilbert space. So let's call that full state psi prime. And then this general result states that this error E is correctable if and only if for the state psi prime, the reduced density matrix on the reference and environment factors just factorizes. So there is, in other words, there's no mutual information in the state psi prime between the reference and the environment. Okay, so this is sometimes called the decoupling principle. And as you can imagine, since it's sort of stated in terms of entropic quantities, at least from a gravitational perspective, it sort of makes things computationally easier or more tractable. So this is the criterion for quantum error correction that I'm going to focus on. Okay, so let's now move on to the setup for the calculation in black holes. So what we're going to do is we're going to study this sort of quantum error correction criterion in a particular toy model for an evaporating black hole, which was constructed in this nice paper from 2019. So the idea is to sort of model your evaporating black hole after the page time, or to model your evaporating black hole as an entangled state between your quantum system B, which is dual to this black hole, and the bath, which I'm calling R here. Now, these states psi alpha, you could think of as states of this quantum system B, which are dual to black holes with an end-of-the-world brane deep in the interior of the space-time. And the label alpha on these states labels sort of an internal degree of freedom, which you can think of as living on this end-of-the-world brane. Okay. On the other hand, the sort of states labeled by alpha on the bath side are just given by some orthonormal basis of states for the bath. Okay. So this then is some entangled state between the quantum system B dual to the black hole and the bath R. Okay, and so the number of terms in the superposition, which is labeled by K, sort of this integer K plays the role in this toy model of the evaporation time. So when K is much smaller than e to the S0, where S0 is the entropy of the black hole. Sorry, when K is much greater than e to the S0, that's the post-page time phase. And this region shaded in blue here, which is in this case the island, moves over into the entanglement wedge of the radiation. Now, to study quantum error correction in this context, we need to introduce what we mean by a code subspace. So we can do that pretty easily by considering some excitations I and I prime, which lie within the interior and the exterior of the black hole respectively. And just to be clear, these kind of states which have some excitation I in the interior of the black hole and some excitation I prime in the exterior of the black hole can be constructed from the dual quantum mechanics point of view with sort of a Euclidean path integral with some sources turned on, and the label alpha on the end of the world brane can be thought of as the sort of boundary condition at the other end of the Euclidean path integral. And very roughly speaking, the dual bulk geometry will then comprise of this black hole with an end of the world brane with some degree of freedom alpha living on the brane, and a state I for the excitation in the interior, and I prime for the excitation in the exterior. Okay, so the main question we wish to address now in this setting is this. After the page point, which is when K is much greater than e to the S0, what kind of errors acting on the Bath Hilbert space, HR, are correctable for the encoding of the interior subsystem, or in particular the island portion of the black hole spacetime?
Hi, Onkar. I had a quick question, if you don't mind.
Please. Yes, please.
So in the previous picture, the left-hand side and the right-hand side, is that a schematic picture, or is there a calculation behind it?
So this is the right-hand picture is schematic, because the left-hand picture is very well defined. what you're supposed to do is, of course, compute overlaps of these kind of states. And then what happens is that at least the 0th order thing that happens is that such overlaps will get filled in by space-times in the bulk, which look like the right-hand side picture.
Right. Yeah. No, I just wanted to, yeah, thank you.
Okay, great. Very good. So the question we want to address then is which errors acting on the bath are correctable for the encoding of the interior subsystem. And as I said before, these errors are going to be modeled by the action of some quantum channel E on this bath Hilbert space. And we've discussed this again, but previously, but let me just remind you, you can model this bath, this quantum channel E by considering some environment factor, some auxiliary environment factor, and then like performing a joint unitary on the environment and the bath. Now, in order to use the decoupling principle for quantum error correction, we need to also introduce reference systems, as you'll remember. And because we have the code subspace has this natural tensor factorization between the interior and the exterior, we need to introduce a reference which also has a similar factorization. So we introduce essentially like two reference systems, one corresponding to the interior degrees of freedom, the other corresponding to the exterior degrees of freedom. And we construct this sort of maximally entangled state between the reference and the physical system, and then act on that with this unitary U, which corresponds to the quantum channel. Okay, so this is the entire state that we are interested in for the black hole. And now the last thing that remains to be done is to just compute this particular mutual information between. So if we were interested in the encoding of the interior degrees of freedom, what we would do is we would compute the mutual information between the interior reference system with the exterior reference system and the environment, and check whether this is 0 or not. So in particular, if this mutual information is 0, then we conclude that the error is correctable, and if not, then not. Okay. But of course, as you probably know, for gravity computations, it is somewhat more convenient to consider Renyi mutual informations instead of the entanglement mutual informations, and then consider the n going to 1 limit in the end of the computation. So that's what we're going to consider. We are going to study these sort of Renyi versions of these mutual informations that we've defined. Okay, so for the rest of the talk, I'm going to like study this mutual information, the Renyi version of this mutual information, using JT gravity, which is where these various black hole states were defined in the West Coast model. So just to give you a flavor for the computation, I'll present one of the terms that is relevant for this Renyi mutual information, and then I'll just tell you what the results are. So for example, if you wanted to compute something like trace of rho prime to the n for the reference and the environment systems together, then you can pretty easily work out what it looks like. And it has this, there are a whole bunch of sums, but the main thing that I want you to focus on is that there are essentially two types of terms inside these sums. Ones which involve overlaps of black hole states, which are written in black, and then all of the information or all of the data about the quantum channel can essentially be sort of repackaged in the form of a particular tensor, which I'm calling F here. And this F is some, again, as I said, this F tensor is a tensor which sort of nicely packages together all of the data about the quantum channel, the error channel E. You can visualize, if you like, this F tensor in terms of a tensor network, which I've tried to draw here. And then sort of on the right-hand side of the spectra, you see these black lines are essentially these overlaps of these overlaps of black hole states. And this blue tensor, the F tensor, which includes all of the data about the quantum channel E, is then glommed on to this picture, if you like. Okay, so the idea is basically to compute the overlaps, the black hole overlap, the overlaps of black hole states by using JT gravity, and then glom on this tensor network coming from the quantum channel E, and then perform the sums. So that's the general strategy. But the one caveat or the one remark that I should make about this calculation is that we are assuming here that this F tensor, which remember had all of the so this F tensor, which had all of the data of the quantum channel E, we are assuming that that does not contain any additional black hole microstate overlaps within it. Okay, because if it did, then it would source additional asymptotic boundaries in our calculation and would lead to other interesting gravitational saddles. So an example of this type of thing failing is when the channel that you're considering makes use of something like the Petz operator reconstruction in the interior of the bath. Okay, because that the Petz operator reconstruction uses these basically introduces additional asymptotic boundaries in your calculation. But on the other hand, if you something like the Petz operator reconstruction is a very highly fine-tuned quantum channel, which would need access sort of to the details of black hole microstate overlaps. And so at least as long as the quantum channel E is fairly generic and does not have access to black hole microstate overlaps, then this assumption is a reasonable one. So having said that, we can now go ahead and compute the various. So for example, we were looking at the computation of this particular trace of rho prime to the n for the reference and the environment factors. So it's now pretty easy to go ahead and compute these things. For example, if the fully disconnected geometry is accounted for in this computation, then you can easily convince yourself by doing these various sums that you find an answer like this, where the DI is the dimension of the interior code subspace, DE is the dimension of the exterior code subspace, and this particular factor here is packaging for you all of the content or all of the information of the quantum channel, or all of the contribution of the quantum channel. In particular, the sigma environment is a particular density matrix. What it is that it's essentially you take the maximally mixed state on the bath and act on that with the quantum channel, and then ask what is the output density matrix on the environment. So the trace of the nth power of that is what appears in this particular computation. So this last piece here is where all of the contribution of the quantum channel is, and all of the contribution from the black hole or the code subspace is distilled out in these two terms. So
just one quick clarification.
Yes.
So when there is an answer, so your original statement was about this quantum error correction type of statement was about pure state. So when you have an ensemble average, that it's acting in the K's, right? In increasing the K at each step or something like that. That's the place where the ensemble averaging of the Hamiltonians will go in, because a unitary is acting on the radiation and some auxiliary system or something, right?
That's right. So what we are doing is we are essentially computing you're completely right. We want to compute this mutual information, but we are computing the mutual information is some number, and then we are using JT gravity, implicitly sort of assuming that we compute the ensemble average of this particular mutual information.
I see. Okay, yeah. Thank you.
Yeah, great. Thank you for that question. So that is the contribution from the fully disconnected geometry. So you can also similarly go ahead and compute the other terms in the Renyi mutual information by similarly considering disconnected geometries and performing all of the index contractions. I won't go through the details of that, but the upshot of this calculation is that what you find is that the Renyi mutual information coming from the disconnected contribution simply vanishes. Okay. More precisely, I should say that this Renyi mutual information is exponentially small because there are other subleading saddles which are suppressed in the entropy. But if you just focus on the disconnected saddle, then you find a vanishing mutual information. And so you would conclude that this particular error is correctable on the interior of the black hole. But you have to be a bit careful, and you also need to consider other, like for example, the fully connected contribution to this particular mutual information. The calculation for the fully connected saddle is a little bit difficult at general n, but we can always work at n close to 1 and then take the n going to 1 limit using the 𝗬𝗵𝗶𝗿 trick. So that computation seems, it turns out to be more tractable. And so what you find when you do the computation using the fully connected, oh, sorry, this is a typo. This should say fully connected geometry. So when you compute the contribution to the mutual information coming from the fully connected geometry, what you find is that that mutual information is non-vanishing. In particular, you get twice the log of the interior dimension. And one thing that I should point out in these various formulae is that they again have a very similar structure, namely that there are these factors which come from the black hole spacetime and the code subspace. And then there is a factor which sort of encodes all of the information about the quantum channel. So in this case, the density matrix sigma that appears is, again, very similar. You feed the maximally mixed state into the quantum channel, and then you read out the state on the bath. Okay, so essentially it's the sort of output state you get when you act on the maximally mixed state with this quantum channel. That is sigma r. So in this case, all of the contribution from the channel is packaged neatly in terms of the sigma r. So the upshot is, so the one last thing that we need to check is when is one or the other saddle more relevant. So it turns out that this question, at least in the n going to 1 limit, has a nice answer. So it turns out that when this particular combination of the entropies of sigma r minus sigma environment is much greater than minus the black hole entropy, then the interior is protected from this quantum channel E. So in other words, when this condition is satisfied, the disconnected geometry will dominate over the connected one, and the error will be recoverable. Okay, so this particular quantity on the left-hand side is what in quantum information theory is called the coherent information of this quantum channel E with respect to the maximally mixed state. Okay, so we learned that you can think of this coherent information as some sort of a measure for how noisy the quantum channel E is. And the black hole entropy provides a lower bound for how noisy it can be until the interior of the black hole gets corrupted by this quantum channel. So this is what I just said. Now, so far, I just considered like the contribution of the fully connected and the fully disconnected saddles. But at least for simple errors like erasure errors, one can actually also resum a whole bunch of planar geometries using the Schwinger-Dyson trick. I don't have the time to go through the details of that calculation, but you can pretty easily show that when you do that, then the mutual information, these Renyi mutual informations rather, have a nice smooth transition from the answer for the disconnected saddle to the answer for the connected saddle with some smooth transition in between. So let me conclude with some final remarks. So in the black hole interior, what we've found is that there is a sort of more robust version of quantum error correction, where even errors acting on the bath or the radiation can be are sort of recoverable, or are the black hole interior after the page time is protected against even a large class of errors acting on the bath. The sort of properties that, or the kind of channels that are protected should not have or do not have access to the detailed details of black hole microstates or their statistics, and have this other property that they shouldn't be too noisy, and sort of have this bound on how negative their coherent information can be. And one last comment is that we expect this robust form of quantum error correction to also generalize to a sort of more general entanglement wedge reconstruction setup, where the regions of the entanglement wedge which are behind non-minimal quantum extremal surfaces, these so-called Python slunge portions of entanglement wedges, we expect that they should also have this sort of robust form of quantum error correction, but that is currently under investigation. But I'll just leave that as a remark for now. Thank you for your attention.
Thanks, Onkar. So yes, two quick questions, maybe. Somdatta?
Yeah, so going back to the question that I was asking, when you are saying that the environment channel can be invoked by pure states, I would guess that if you say, suppose you exchange something with the environment, it's going to not remain the same state, right?
Yes.
So then how can you say that it can be invoked by a pure state?
So what I said was that so you bring in the environment in some auxiliary state and then couple it to your original density matrix. What the state that you bring in, see the initial state of the environment which is brought in this that auxiliary state is what I was saying can be always taken to be pure by a choice of what you mean by the environment. So what happens after the coupling is turned on is just completely up for grabs. I mean, that depends on the specifics of the channel, the specifics of the coupling, and so on.
So you take that into account?
Yes.
Okay.
Alok?
Hi, Onkar. So, so the original, this quantum error correction, I mean, the simple way to understand it was like subregion duality, right?
Yes. Yes.
So is it correct to say that the main message of your talk is that if we have this new, QES where the island moves in the entanglement wedge, then there is a subregion duality that can be now implemented via some logical I mean, so the same thing holds, but now with this new entanglement wedge with the island has moved in.
Yeah, great, thank you. I think it's more than that. I mean, the subregion duality in this case would say that the island is encoded in the radiation and therefore is protected from errors on the dual quantum, the quantum system B that's dual to the black hole. That's of course very easy to check in this case, and that's absolutely true. But what I was focusing on was a sort of more robust form of error correction, where even when the island is in the entanglement wedge of the bath, there is a class of errors on the bath.
Okay, additional errors. Yeah.
Exactly. There are more. It's sort of more robust because there is a class of errors on the bath itself, which are protected against. So that's the kind of thing I was.
Yeah. But certainly, as you're saying, it's true that they are protected against the errors in the CFT.
Yes, that's easy to show.
That's easy to check. But then your last statement was that. So is it? I mean, is a corollary of your result that there are some interior operators which we can reconstruct through this, and they are independent of the microstate geometries? I mean, as you were saying that these recoverable channels are independent of the microstates of the black hole, right? So I was asking in the context of the mirror operator construction of Suvrat and others, where it seemed like you would need the knowledge of the microstates, right? In that case. Yeah.
That's right. So operator reconstruction usually does require a detailed knowledge of black hole microstates. What I was saying was that the kind of channels which this encoding is robust against do not have this, are ones which do not have access to black hole microstate details.
I see, but there are also some operators. I mean, could I not think of them as operators in the bulk, or do you think that's not the right way?
I think they're exactly. So I think they do not. So these kind of channels are sort of fairly generic, and because they don't have access to black hole microstate statistics, they don't introduce excitations in the interior of the black hole.
I see. Okay. Thank you. Thanks.
Sandeep?
Yeah, Onkar, thanks for a very nice talk. I have a feeling I have not understood one of the key points you were trying to make. So let me ask you,
Sure.
which is, was there a sense in which the errors are better protected in the radiation than if we were just trying to reconstruct the bulk from the boundary in just standard ADS-CFT
Yes.
quantum error correction? And what is that sense? I didn't understand.
So for example, if you just have the ordinary, you say you're in vacuum ADS, then again, if you have a boundary subregion A, then there's a bulk entanglement wedge that's dual to it. Let's say it's just some interval in ADS3, right? Or ADS CFT2. In that case, this doesn't work. So the code subspace degrees or like interior degrees of freedom in that entanglement wedge are not robustly protected against generic channels acting on the boundary. This is very easy to show. And it's not a surprise because, in that context, what is true there is that errors acting on A bar are robustly protected against. But here, what is happening is that you have a slightly more robust version of quantum error correction because the entanglement wedge lies behind a non-minimal QES. So it's a slight, so it's like, so there's a different flavor to this kind of entanglement wedge. And that's what gives rise to, in my opinion, that's what gives rise to this more robust version of quantum error correction.
I see. But then just to ask, I mean, in the standard ADS situation, you are protected against erasures
of A bar.
Of A bar.
But not on, so generic errors on A will not be protected against and will.
And I see. And here, even fairly generic errors in the radiation are protected against, huh?
That's right. As long as they're not fine-tuned and they're not very noisy. Where the noise is characterized by this black hole entropy.
I see. Okay, thanks a lot.
Sure.
One last question. Maybe okay, two. Deepan, quick question.
Yes, sir. So in the case of binary black holes, if the interiors of the two black holes interact, then how will the error calculation be modified?
So if I understood the question correctly, you want to have like a thermophile double kind of setting, like where you have an entangled pair of black holes?
Yes, sir. Yes.
That's a good question. That's a good question. I think that there is that you should be able to construct a similar bound of so in that context, I suppose you want the error channel to act on one of the black holes and ask whether that is so the one difference in that context is that there is at least if the entanglement between the two black holes is sufficiently simple, then you don't have you won't have, like in the simplest case, you won't have a Python sludge. So you might not have a very like this kind of robust form of quantum error correction. But on the other hand, if the entanglement is generic and you have some kind of a Python sludge portion for the dual geometry, then I would expect that there is a similar robust form of quantum error correction inside only in the Python sludge portion of the geometry. That would be my guess, but I'd have to think more about your question.
Okay, thank you, sir.
One last question, Abhijit.
Yes, thank you, Anirban. Thanks, Onkar, for a wonderful talk. Just to put this in, just to see whether I understand the context. So, is it true that a more traditional understanding of the black hole, of the Hilbert space corresponding to this picture, going back to Hawking, would have told you that this is protected, right? The error should be protected, right? Which is reflected in the fact that the disconnected geometry dominates.
Yeah.
Now, with the newer understanding, you see that there is a possibility that the errors may not be protected, and you find the precise condition for which that is the case. In particular, the properties of the channel for which the errors are not protected, right?
That's right. That's one way of saying it. But what I would have, the slightly different way of putting it is that the new thing as compared to Hawking is the understanding that the island portion of the black hole spacetime is now in the entanglement wedge of the bar, after the page time, right? So that is the first step of where the novelty or the departure from Hawking comes in. But what we are finding is that even so, so you might be a little bit uncomfortable with this statement, because it seems like, if it might seem like it sort of blatantly violates the causal structure of space-time. But what we are saying is that, or finding is that, this encoding is somehow surprisingly robust, and not everything, or the sort of fairly generic things that you do on the bath do not affect the excitations deep in the interior of the black hole. So it's that the robustness of the encoding, that sort of robustness of the encoding is what we are trying to capture.
I see. So even after page time, when it is
even after
entanglement wedge, you would have naively thought that the errors would not be protected. Yes. So that's another kind of way of looking at it. I see.
Yes.
Thank you.
Yes. Yeah.
Okay, I guess that's it for the morning session. Thanks to all the speakers. So we'll continue with questions in a discussion.